Okay, Elise, I'm starting here on page 41 in the seminar book, and the Lexis diagram is just straight lines of slope equals to 1 with different y and x intercepts on it, but they all have slope equals to 1, and you follow along one of those lines to approximate on your differential equation that you're going to set up. So they have U of AT as a density of females of age A at time t. Females of age A at time t, and at a time delta t later, all the individuals who are still alive will have aged an amount delta A equals to delta t, and so what they're going to do is write this equation at the next time, A plus delta t, t plus delta t is going to be where you were before, U of AT, minus, and they call this amount a D, and they say D is a mortality function. Mortality function for those at age A. And so you're going to subtract off those that died in that interval who were alive at the previous time, and how much of that interval time that they have, and then this is an O of delta t squared, so this function right here has some other terms involved in it, but when you take the limit as delta t goes to 0, these are going to go to 0 after we divide out our delta t. And they specify that D is a mortality function, dA delta t plus O of delta t squared is a probability of an individual of age A dying in the next small interval of time. So what they're going to do is they're going to say, using dA, we're going to use dA equals to delta t, and we're going to expand using, they use a Taylor series, they say, and you get the, well, let's look at it. If you have du dA plus du dt, so now you have to take your, I'm going to do this a little bit differently. I'm going to take the original equation up here, this one right here, and I'm going to subtract off U of A plus delta t, t plus delta t minus U of AT. I'm going to leave this equals minus D of A U of AT delta t plus some O of delta t squared. And then if I divide everything by the delta t, what happens is this delta t and that delta t are going to go away. This first equation over here on this side is going to look a little bit like a derivative. In fact, if you were, this is a part that they say if you were expanding using a Taylor series, well, just think about taking the derivative of it. If you were looking at du dA, that's going to be your derivative of du with respect to A, but I have with respect to t right here. If you want to replace that with the t, they told us that the delta A is equal to the delta t. Let me get my notes that I've written this out all on. write it this way, and then what you get, u of a plus, remember the delta t is a delta a, u of a plus delta a, t, and then what I'm going to do is subtract off my u of a t, and then that first term right here, that is, I need to compensate for that one again, so I'm going to subtract it because I added it on. But now what I'm going to do is I'm going to add to it u of a plus delta a, t plus delta t. And this is all still over my delta t. Now if I look at this first part, I'm going to put this on full screen mode so that I can get my pens for me. Oh, that's too small. We're not going to do that. You won't be able to read that. If you look at this first part, I'll just change this color here. That over the delta t, you know that delta t is equal to a delta a, so I can split that apart and I can write that over a delta a because delta t is equal to delta a. So this would be u of a plus delta a t minus u of a t, and delta t is equal to delta a. So I put a delta a there, and there's your partial of u with respect to a. Or if you will, you can write it this way, times the delta a over delta t, if you will. But delta a and delta t are equal to 1. You can do it either way. And then if you look at the second grouping over here, these ones right here, the a plus delta a is the same on both of these. So all we have to look at is the t and the t plus delta t. That's going to give us a change in t. We write the second one first, and then that gives us our u of a plus delta a, t plus delta t, minus u of a plus delta a, t, all over our delta t. And now that second one is a derivative with respect to t. So this just becomes our derivative of u with respect to a plus our derivative of u with respect to t, which is exactly what they were trying to get to. On the other side of our equation right here, well, let me get this in a different color too so you can see it. On the other side of the equation over here, we have this stuff right here. We're going to bring that down. Notice we have to take some limits, and when you take the limits, this O of delta t squared becomes an O of delta t, and as delta t goes to 0, that goes to 0. That's what that capital O notation means. So we are left with then, this is equal to minus d, a function of a, times u of at, or you can write it as du dA plus du dt is equal to minus d times u. This is not a derivative. This is d times u, a differential. Notice that we use the Lexis diagram in the fact that we used our delta t equals to our delta a. This is what's giving you those slopes, unit slopes on the Lexis diagram. That's why you have to use that Lexis diagram. Along these lines, then, they give us some initial conditions. So our initial conditions are u of a0 is equal to u0 of a, and that's equation 1.11.41. we are assuming that 0 is less than or equal to a is less than or equal to some omega, and t is greater than or equal to 0. That's our assumptions there. Omega is the greatest age in the population with initial conditions given at time t equals to 0. So omega is defined, I'm not going to write that all down, defined page 41 bottom. Okay, so turning the page to the next side, what we want to do is try and figure out what their next equation is. It says births enter as a boundary condition at age equals to 0. And so they call that u of 0t. At some time t, someone gets born, and their age is 0, so it's 0t. And they're going to call that to be equal to the integral alpha to beta u of at, so some age, so these are the people that could give birth, and then m of a, the maternity function is m, and then you're integrating with respect to a. So this is like the rate of giving birth, maternity function. Alpha and beta are the youngest and oldest ages for childbearing. So that's going to be the boundary conditions that we need. Now, scrolling down, we want to look at example 1.5. The first paragraph tells you what they're going to do in the example, and then the second paragraph, that big old huge paragraph with all the equations in it, is how they're doing it. So I'm going to read that first paragraph, and then we're going to work through the second paragraph. It says, assume temporarily that u of 0t is equal to b of t is known. So assume that you know this function right here. We're going to solve the Mackendrick's equation, 1.11.40, which is our partial differential equation that we had, this one right here. We're going to solve that equation with this initial condition and the initial condition 1.11.41, which are these conditions right here, to obtain an equation given in 1.10.35. So you have to go back to a previous section to find the equation. And they give the function L of A, and we'll worry about that in a minute. And they say you can refer to section C.1 in the appendix to see how this is done. Mackendrick's formulation may therefore be reduced to a continuous Euler renewal equation, as in section 1.10.2. Don't worry about that Euler renewal equation so much. We're just trying to understand how to solve this. So let the characteristic curves of equation 1.11.40 be given by A is equal to, we're going to call this some A hat of S, and T, we're going to call this function T hat of S. On these curves, we're going to define U hat of S to be equal to our U of A S, that's supposed to be A of S, A hat of S, and T hat of S. So they're going to plug in their characteristic curve into U. By the definition of the characteristic curve, they're going to say the partial differential equation reduces to an ordinary differential equation. Well, let's see why. Let's calculate du dA plus du dt. So du dA is going to be du, we can take this down to a du ds. They call that a du hat. So let me start with that du hat. I'll start where they start. It'll make a little more sense. Du hat ds then is going to be equal to du dA, these are all del's, these are our partials, and then dA, and these are ordinary differential equations, dA ds, those are ordinary derivatives because A only depends on S. And then we have to take the partial of U with respect to T, so du dt, and then dt hat ds. And that right there, if you, first of all, make sure you understand how I went through the differential equation. You have to take the derivative of u. Our u hat is our u, so I just use our u notation right here. Du with respect to a, well, a is just our a hat function, so I'm sort of interchanging the dA and the dA hat. Don't be too confused about that. That's just a notation that they did, but it's following through on the derivatives that they have. Let me pause this a second. I want to open to the appendix. I need my hands free. Well, just wait a second. It's not letting me pause it. So let me get to my appendix. Okay, so I was just seeing why they wanted us to look at the appendix here. They're just, well, we might make it to the appendix, but I don't think we need that right now. Okay, I just wanted to verify that. So we have our derivative taken here, our partial derivative. Note that the u function is the same one we had before, so I know that du dA plus du dt has to be equal to minus d times u. So that is what we're going to actually plug in for this equation. Set these two equations equal, because these are going to be the same values. You can get your equation then du hat ds equals minus du. Sorry, this is a full derivative, not a partial derivative. That'll help you. I get those symbols interchanged all the time. I don't know about you. Okay, so if you look at this, you have du hat ds equals to minus du. I've found where I am again. If you compare this with the equation 1.11.40, our equation 1.11.40, I'm going to draw this in red so that we can find it. That is this equation right here. If you compare those two equations, what they're going to say is this. The dAds or dA hat ds in this case has to be equal to 1 because they're the same equation, and I have this dAds term here, and it's like having a 1 right there. Similarly with the dt hat ds, you also get that to be equal to 1 right there. So then if you solve those two equations, you are going to be able to have, if you solve these three right here, you'll get your solution. So if you look at the first one that I actually did was the du ds. In my notes, I actually did that with respect to t. It doesn't matter. If you want to solve du hat ds by separation of variables, remember this d is not a differential. It's not a derivative. So we're going to divide the u over, and that's the same thing as our u hat, our u equals our u hat in this case. So I'm going to have a du hat over u hat is equal to minus d times s. Integrate both sides of that, and you get the natural log of the absolute value of u hat is equal to minus s. And we're going to need some initial conditions and boundary conditions on it. So this is going to go from u of a0 to u of at. And so then this is equal to, let's just leave this as minus the integral of d times s. What happened to my d? I multiplied by my ds, I get a minus d times ds. Remember, this is d as a function of a is a function of s. So we don't know exactly what that integral is going to be, we just write it down. And don't worry about it right now. What that is going to give you then is that you get minus integral of d, let me not put the ds in parentheses, ds is equal to this natural log. And if we're trying to solve that, then you do e to both sides of it. Maybe I should do my initial conditions first. I keep forgetting about the initial conditions. So when you plug that in, you're going to have your natural log u of at minus the natural log u of a0 equals minus the integral of d ds. Now do e to both sides of your equation. You get e to all of this is equal to e to that. But when you split this apart, you're going to get u of at I really would like that to be added to the other side. I skipped a step in my notes. No, it has to be multiplied. It's not added. It is so true. You're going to have e to this and then e to the negative of this part right here, which is going to be, let me write it out. You'll have e to that and then e to that. If you see what's happening, this e and this e are natural log are going to cancel. You get u of a t over u of a0. It's positive, so we don't have to worry about absolute values or anything like that. Equals e to the minus integral d with respect to s. Multiply both sides by your u of a0, and you get u of at is equal to u of a0 e to the minus integral d with respect to s. That is your u of at function. Now we have to do the same thing if you're integrating your, well, let's read and see what they do after that. Yeah, let's go ahead and integrate the dt ds one. You have dt hat ds is equal to 1, so that says dt hat is equal to ds, and you integrate both of them, and that tells you that t hat is equal to s plus your s0, your initial condition, whatever that is, and that gives us our t hat as a function of s, and you're similarly for your a hat is going to be some a plus some a0. Oh, some S plus some S0. But it's some other S0 from the first one. It's some initial condition for that. Now, it says the characteristic curves are straight lines or unit slope in the positive quadrant of the AT plane, and the initial S equals 0 conditions that we need to apply depend on whether they intersect the A-axis or the T-axis, as in the Lexus diagram of figure 1.12. If T is greater than A, then they intersect the T-axis when S equals to 0. So if you go back and look at your Lexus diagram, I'm not going to draw it here, but go back and look at your Lexus diagram. They almost have an entire line for A equals to T. That would be your line going all the way. If this is your 0, 0 point, this would be your A equals to T line. And this is your T-axis down here. This is your A-axis up here. And it says if you have the initial condition x equals to 0, if T is bigger than A, so if you're down here someplace, then if you follow your Lexus diagram back, you're going to intersect your T-axis. And that's what they're trying to say. You intersect the T-axis when S is equal to 0. So that would be the age of the person equals to 0. If we parameterize the T-axis by T equals to tau, A equals to 0, then the conditions for T hat, A hat, and U hat at S equals to 0 are T. So we're just going to say that T equals to tau when S equals to 0. So if I go and look at these equations right here, at S equals to 0, you're going to have T of 0 has to be equal to, our T hat of 0 has to be equal to tau. Our A hat of 0 is going to be equal to 0 because you're not up, you're down on the T-axis at some time tau. Right there on your T-axis, that's what's happening. And your U hat of 0 has to be your B of tau function because that's your birth rate function. But the B of tau is just U of 0 tau, and that's going to be, you just do the integral alpha to beta of U of A tau and M of A dA with respect to A. And so what they're going to do is they're going to look at these integrals that we did for T hat and for A hat right here. And for U hat, with those initial conditions, you get A hat is equal to S because at S equals to 0, this ends up being our 0 value right here. And T hat at 0, you get S plus tau. So this S0 right here becomes our tau. And U hat, then our U of we're going to say when A is going to be equal to 0, then you get your U of 0 tau. So let's actually look at that one. Let me get another piece of paper added on here. So let's go back and pick up we had our U of A, oh, I can make this go away, give me more room. U of A T, well, they're writing it U hat of S. S is a function of, where did we write our S? Oh, A is a function of S and T is a function of S, so then you can write du with respect to S. So we can call this our U of AS because A and S depend on it. So U hat of S is going to be equal to, now they claim this is a B of tau e to the minus s, e to the minus integral from 0 to s, and now they say d, instead of this being of a of s, they just called it an s prime. They did a u substitution here. This amount right here comes from plugging in our b of tau for our u0 of tau. So when we go back and look at this integral up here, I had done it with respect to a at time 0, but then if we said a is equal to 0, then you get u of tau, well, u when a is equal to 0. Okay. Let's go down here. So that gives us our b of tau. Now, what we want to do is to figure out how they get that to be some L of s. They set it equal to b of tau, L of s, and they're going to define L of s. Because remember, they're trying to make it look like that equation from section 1.10. And so they're trying to define what L of s is. If you set that equal and you want to define L of s, that means L of s has to be equal to that function right there. Now, if we're looking at this function, then if you just want to change your variables, if these have s's and you want to change it to a, it doesn't matter. That's exactly what they say next. And that makes L of a equal e to the minus, and you're going to integrate from 0 to a, and you're going to have d, change a variable. It doesn't matter what you call the variable. They're going to call it b. And then with respect to b, this is not a derivative. You're integrating this function. This is the death rate. The death rate is a function of b, and then you're integrating with respect to b. They just changed the variables there. They could have called that t, they could have called it s and been done with it. They want to change this back then to the original terms. So how do you get back to the original terms? Let's look and see. If you look at the original variables of a and t, we had u of at. Now, this tau was our parameterization. Did I write it down or not? No, I didn't. The tau is our parameterization for when s equals to 0. That came when s was equal to 0. We said that that was the tau. Well, if you want it just in terms of a and t, then you just have an a minus t as the shift on it. So let me see. If I write this, I'll just write it this way. B of t minus a, that's kind of our shift, times our L of a function, because that was our tau. Now we need to be a little bit more specific about how that tau is defined. So I want you to make sure that you understand where that's coming from. This, of course, is when t was greater than a. So we were down low in the Lexis diagram. The line intersected down here at some s equals, the s-axis equals to 0, the t-axis. And then they're going to parameterize the t-axis, so then they're going to say at t equals to tau, that's what we're going to have right here, we're going to have an a equals to 0. So that's really just the point ta, but we called it tau 0. So we're using the point ta, and we're going to mark that to tau 0. How do you get Wait, do I have that right? Let me think about this a minute. This really should be a t and a 0 on the a-axis, so a is equal to 0 there. And if you were up here at some other t, call it a t1 and an a, some value, if you want to do the shift down, you're going to have to subtract. You're on the line, that's where it's coming from. Remember, your line has slope equals 1, so then that means that if you're going through this variable tau 0, the line through tau 0, that line through tau 0 is going to be, with a slope of 1, is going to be a is equal to t, but we want it shifted to the right, t minus tau. Then when you plug in tau, you're at 0, and that gives you a slope of 1. But I need a t minus a. I almost have it. Well, bear with me a second. This is a part I actually didn't write down. It did come to me. Oh, it's actually even easier than that. They're going to rename the variable. Let's look at this a little bit bigger. Forgive me, I should have written this part down first, but I'll show it to you. You have t greater than a. So then t minus a is going to be bigger, t minus a is going to be bigger than 0. So they're using this parameterization right there, t minus a. And that's what they're using to call tau. And so when a is equal to 0, it's going to be down on the axis. When you're going to be down on your x-axis. So you're actually looking at b of t minus a, L of a. And if you're looking for the other direction, which they're going to leave for you to do, that's going to be where you have t less than a. And so you actually look at a minus t in that one for your parameterization. It's just a little bit different parameterization. But that's what you're going to be calling your tau variable, is going to be that. That gives you your u of at is b of t minus a, L of a. You are going to do... You show the last sentence of that paragraph. I think sentence is spelled E-N-C. The rest of it then is just a little bit of a discussion about your survivorship functions and the graphs, the type 1, type 2, and type 3 on the graph. Your questions that you are trying to work on answering are going to be just changing your equation a little bit and being able to solve those equations, interpret it biologically. So that is our goal, to be able to get through those questions here this week. On Monday, I will be giving a talk about what your paper is supposed to look like and what your presentation is supposed to look like for the oral presentations, and then we're going to be starting writing. So this week through the beginning of next week is the end of the research, and then after that we are writing. You won't have anything that you have to show on the board on Monday. I will be giving a talk on Monday. So we just need to make sure we get through these problems and that you understand them and can write them up in a paper. Hopefully this helps. Sorry that it's a little bit discombobulated, but that was the easiest way I could think of to do it.